Welcome to Lesson 14B, Practical Application, Jet Engine Afterburners, Part 1. This is the first of a 4-part series to end this lesson series, and we have a special guest lecturer, a good friend of mine, Glen Coates, who at the time of this recording is a lecturer in the Aerospace Engineering Department here at Penn State. So here's Glen to tell you a little bit about himself, and then give you part 1 of this series.
Hello everyone, I'm Glen Coates. I'm a mechanical engineer by training, and I've practiced engineering in the aerospace industry for 45 years. In all, I've worked for 3 different Fortune 500 companies, and one of those companies was Pratt & Whitney Aircraft. At Pratt & Whitney, I spent 10 years designing and developing jet engine afterburners. Now, the reason for showing you today's presentation is more than any other product line, jet engine afterburners capture the essence of the material taught in the compressible flow course. Afterburners are the practical application of compressible flow, and in this presentation I'm going to attempt to bring this material to life for you. Now, the structure of this presentation is going to be done in 4 parts. The first part is jet engine basics to set the stage for things. Then we'll talk about the components that go into an afterburner, and then afterburner compressible flow and thermodynamics, and finally I'll show you some interesting footage of the SR-71 Blackbird. It's a reconnaissance aircraft that was designed back in the late 50s, and it was way ahead of its time. But it was a marvelous, very interesting design. Jet engine afterburners. This is an application of compressible flow for ME420. Now, in this first presentation, we're going to be talking about isentropic flow, Rayleigh flow, Fano flow, and shocks, and then incompressible flow. Jet engine concepts. First, we look at a jet engine cross-section. What is an afterburner? We'll talk about the Brayton cycle, which is the thermodynamic cycle for this engine. Then we'll look at the thrust equation, the afterburner pros and cons, and then videos for an aircraft carrier launch and recovery. All right, jet engine basics. This is a cross-section of the jet engine without the afterburner. You have the cold section on the left, the compression section. Then the hot section begins where the combustor is in the center of the picture. And finally, the engine exhaust. We'll look at more of these components in a minute. All right, the ideal Brayton cycle for a jet engine, and 4 parts. First is fresh air coming in at station number 1, looking over on the left in the picture. And then fuel is added at the combustor, and the discharge of the combustor goes into the turbine, where the high pressure gas is expanded to extract work. And if you look at this on a PV diagram in the center of the picture, at station 1 we have the fresh air coming in, and because this is an ideal engine, we have constant entropy as it goes through compression to stage number 2. And then the heat is added between stage 2 and 3, and then finally an isentropic expansion of the flow from station 3 to station 4. And similarly, if we're looking at the TS diagram on the right in the picture, station 1, once again at the bottom, we add compression energy through the compressor from station 1 to station 2, and then constant pressure heat addition from station 2 to 3. In reality, it's not constant pressure, of course. And then from 3 to 4, an expansion, so the temperature drops down to lowest discharge. Jet engine thrust equation. We want higher throat gas temperature because that increases the gas velocity, and of course that gives you higher engine thrust. Now, the gross thrust equation is very simply on the first line. The gross thrust is equal to the mass flow rate of the exit gas minus the mass flow rate of the inlet gas, and each times its velocity. And then we've included a pressure term, P exit minus P ambient, times the nozzle. Now, if you fully expand, you maximize the thrust. Take a look at the picture on the right. Thrust is optimized when the ambient and the discharge, the exit, are 1.0. So if we eliminate that term, assuming we're fully expanding the exhaust, now we have the middle equation. The gross thrust is mass flow rate times its velocity, and then at the inlet, mass flow rate times its velocity. Now, because the fuel flow rate is fairly small compared to the air, as in about 2 or 3%, you could say that it's constant mass flow. So the gross thrust is mass flow rate times the exit velocity minus the inlet velocity. Now, for a choked flow at the nozzle, the maximum thrust is achieved when Mach number is equal to 1, such that the velocity at the throat equals the sonic velocity, and that is equal to the square root of gamma GRT. The G, of course, is because we're in English units. Now, taking a look real closely at these 2 terms in the gross thrust, we have the gross thrust is equal to a constant times 2 terms. One is the mass flow rate, and the other is the square root of the temperature. And looking at that equation, we can see that if we double the mass flow rate, you double the thrust. And if you double the absolute temperature, T, in the equation, you only get 40% increase in thrust. That's basically the square root of 2. So we see that there are two ways to increase the thrust, and you can either increase the flow rate or the temperature, and there's a better return for the mass increase. Now, we have to recognize that there are limits on the temperature rise that we can get from the fuel. We have a graph over here. On the x-axis is the equivalence ratio, that's the fuel-air ratio, and on the y-axis is the flame temperature. And these are the flame temperatures for various fuels, methane, nitromethane, kerosene, and so on. And you can see that they all tend to peak out at the equivalence ratio of 1. And these are the actual temperature rises. What happens in theory is that if you look at the dotted red line, as we add more fuel, there should be a linear relationship for temperature increase. But it doesn't work out that way because the gas has dissociation, and so the actual temperature rise is less. Now we'll look at the two key points on here. Notice that at the equivalence ratio of about 0.3, that means about 30% of the amount of fuel that you could put in the flow, that's where a main burner operates. And the equivalence ratio of 1.0 is where an afterburner works. Now, the method of increasing thrust affects the propulsion efficiency of a jet engine. Over on the left we have a picture of a jet engine, and on the right we have a turbofan, and they're very different in terms of their propulsion efficiency. On the left we have the jet engine that's operating, and you can see in the graph below it says for this format the temperature is very high in the exhaust and the velocity is very high in the exhaust. So it has a very low mass flow rate, but the temperature and velocity are considerably higher. And what that tells you is that looking at the exhaust out of the jet engine, there's a lot of energy that goes out the back and we can't recover it once it leaves the plane of the nozzle. Now in contrast, if we take a look at the right hand side, we have a turboprop engine, and in this case everything is turned around. We have high mass flow rate, we have low exhaust temperature and low exhaust velocity, so the amount of energy that is lost out the back end of this thing behind the propeller is much smaller, and it has therefore higher propulsive efficiency. Now there are some practical limits to the thrust that you get from a jet engine. First of all, the materials. There is a maximum allowable turbine temperature. In other words, the fuel can get much hotter than the metal can tolerate, so we have to limit that in the main burner. And then there's the chemistry limit. As the fuel-air ratio approaches stoichiometric conditions that we saw in the last curve, the temperature rate of increase is curtailed because of gas dissociation. And then there's the physics limit. Gas velocity in the throat is determined by the square root of temperature, and that is the Mach number is limited to 1.0. And finally, the thermodynamics. High exhaust gas temperatures and velocity means lots of energy is lost, and it's a drop in propulsive efficiency. Now, comparing the practicality of a jet engine, the advantages of afterburners are there's a significant increase in thrust, and you get this increase in thrust with a very small weight penalty, and there are very few very simple components that are involved. Now, the disadvantages are equally important. There's a substantial increase in fuel burn and low propulsive efficiency. There's also a significant reduction in aircraft range because of the higher fuel flow rates. And there's also substantial time and effort required to develop one of these things. The problem is afterburners don't scale. You can't make a quarter scale jet engine afterburner and expect it to behave like a full scale one. So things have to be done trial and error and in full scale. So the bottom line is afterburners are used in the military but not for commercial applications because the TSFC, thrust specific fuel consumption, the equivalent of gas mileage in a car, is horrible for a jet engine using the afterburner. Now the military uses jet engine afterburners in a number of situations. Number one, they provide a sudden burst of thrust for takeoff with heavy loads on board, a short takeoff distance, for example, with aircraft carriers, and to achieve supersonic speed, and also evasive and combat maneuvers. That's when these are used. Now what I'd like to do is to show you a video clip of a jet taking off from an aircraft carrier. The launch only takes about 2 or 3 seconds, and the afterburner lights up as soon as we take off, as soon as we get over the edge. Now, the takeoff speed of the jet is about 170 miles an hour, and it has to happen within about 300 feet. So the pilot experiences somewhere in the range of 2 or 3 Gs. And you notice there's a deflector in the back there to keep it safe for personnel. Now, just to put this in proper perspective, it's 300 feet where you go from 0 to 170 miles an hour. To bring this a little closer to home for you, if you could sit in a chair on a football field right under the goalpost And then somebody lights off an accelerator, and we see that in 2 to 3 seconds, you're going 170 miles an hour when you reach the other goalpost. It's hard to imagine, but that's exactly what happens. Here's a jet just about to take off. Now you notice the smoke, what appears to be smoke in the base there, that's actually a steam catapult that's assisting takeoff. It turns out even though the afterburner could be on at this whole time, it's not enough thrust to get the acceleration we need. There goes the afterburner, you can see it. And it's on just long enough to make sure that we clear the deck. Now in this video section, what I'd like to do is to show you the actual hookup of the steam catapult. It grabs the nose wheel on the aircraft and provides most of the force to get this aircraft in the air. So let's take a look. Now we're going to hook up the steam catapult, it's shown in the video here. Now in this video clip, what I'd like to show you is the recovery of an aircraft on an aircraft carrier. Notice at the bottom here there is a little hook that's dragging. Imagine this now, you're traveling at about 170 miles an hour and you've got to get down on the deck just right so that this hook engages a tripwire that's on the aircraft. And it's going to look like this. Okay, you see the hook come down. Oh, here we go. There it is. Now as you notice, it's a very, very short recovery time, so the g-forces that the pilot experiences on acceleration and deceleration are very different. With deceleration, it's even bigger than it is on acceleration, and it's already 3 times the gravitational force. Now what I'd like to do is also show you a video clip of a pilot doing a recovery on an aircraft carrier, and it's a view from the pilot, which makes it kind of interesting. Here we see the pilot coming in, approaching the aircraft carrier. Look at the perspective that he's got to keep an eye on. He's coming in sideways, and he's going to have to land precisely on a very small piece of real estate right in the middle of the ocean. You can see the slip trail of the aircraft carrier, and he has to land precisely at the right elevation and the right speed and the right axial end elevation. And you should notice that, and it's not clear in the video, but as soon as he hits the deck, he goes to full afterburning. And why is that? If for some reason he doesn't engage properly with the hook, he has to keep right on going. Summary of Afterburners Part 1. Number 1. The higher exhaust gas temperature increases the engine thrust. The thrust increases as the square root of the gas temperature, and so if the absolute temperature is doubled, you only get a 40% increase in thrust. And exhaust gas temperature is limited by the turbine materials, physics, and fuel chemistry. Afterburners allow higher exhaust gas temperatures, and they significantly boost thrust, but it's a substantial cost in fuel usage.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.